So any homework, any person who tries to upload beyond that won't be able to upload. And then, yes, I don't like to do administrative stuff, so let's try to avoid getting into administrative hassles and whatnot. And okay, that's the homework. Unfortunately, well, it's a matter of perspective. Unfortunately, second homework, which was supposed to be released right now or maybe by the end of the class, it's not yet ready for release. But please don't feel disappointed. It will be out maybe soon enough. And we'll try to keep that one similar in complexity to the first one, maybe not as long. We'll see, but you'll have sufficient time to do it. And what is really important about the homeworks is you don't necessarily have to fully nail the problem. What is really important is the way we select problems is to take you through some of the things that you might need to do to solve this problem. For many of you, you might be forced to read a lot of the additional material. And maybe as the course progresses, to do the homework, you might have to go through maybe 5 to 10 papers after scanning the web. But the point is, these are like mini versions of research problems. So it's just good to play with them. And again, don't be shy. Ask questions, collaborate, discuss with your peers. And if you still think that, okay, you feel uncomfortable asking questions on the Google group, just tell your TA, I'm more than happy to run this in an anonymous forum so that you can post a question anonymously. That's perfectly fine with me. Because the more you discuss, then you'll see that, okay, you've been following the wrong approach, and suddenly after discussing with somebody, or just the mere fact that you try to explain your approach to somebody might help you get the solution. So let us know if you prefer an anonymous forum which will encourage you to discuss. We are willing to set that up. I'm not hell-bent on Google. Okay, then.
Why don't we have a show of hands right now? How many of you prefer anonymous discussion?
Like Piazza or something. Or it doesn't really matter. See, the thing is, by raising hands, you're violating anonymity already. So, anyhow, because it means okay, so rather than give you, rather than just go through another poll, we will set up an anonymous forum anyways. If you don't use it, well, the forum will eventually evaporate out by the end of the semester, so it doesn't really matter, but we'll set one up anyways. And if you're under the cloak of anonymity, that's perfectly fine. Okay, so today I'm going to talk, so this continues where I left off, and maybe to give you a little bit of continuity, where I left off, I mentioned a class of optimization problems, including ones which were called conic optimization problems. Then Alex looked at using a special conic optimization problem called semi-definite programming to actually tackle an NP-hard problem. And that is quite a common strand, looking at relaxations of NP-hard problems, solving them via semi-definite programming. And of course, people who are familiar with the theory literature know that it's even done now. People still have difficult problems. It used to be a trend to always find a linear programming relaxation when linear programming was in supreme vogue. And then, in some sense, Goemans and Williamsons revolutionized the convex relaxations that people used to use by suddenly after that everybody was doing SDP relaxations. And these days some other higher, fancier versions of relaxations are going on. Maybe we come to those, maybe not. But they will be, a little bit of, because the course is trying to cover two important topics, but there's somewhat of an eclectic mixture. You might have to do a little bit of context switching, but hopefully it shouldn't be so bad. Because in some sense, the material that we are covering, both types of material, randomized methods, probability theory, and concentration bounds and whatnot, and optimization, duality theory, optimization algorithms, etc., these are kind of common tools that you should know about to easily understand a lot of machine learning research papers or even optimization research papers. And also for those of you who are starting out in this direction, it'll really help you accelerate the speed at which you start doing research in those areas. Okay, today, even though it's called advanced, today it's not a very advanced day, but the topic is extremely important. The advanced part is, you can say, related maybe to a class project. The theory of duality is most properly developed so far only really for convex optimization problems. I mentioned, when I mentioned the theory of Fenchel conjugates, I mentioned an open problem of coming up with theory of conjugacy for those metric space convex functions. So that's sort of an open problem. And as soon as you start building theory of Fenchel conjugacy in that space, we could extend some of the power of duality theory to that space. But that's quite an open-ended question. Today we will largely stick to the comforts of convexity because of the detailed duality theory that we have. Oops, don't escape. And so just to common definition, I made some slides because there was a lot of material, so I just took some of the slides that I have and improved them to have this reference material for you. So try not to focus too much on that. That's going to remain on the screen during the lecture for you as reference. I'll try to go through some of the material on the board here. But just to define some common terminology, we are trying to minimize. So on this slide right now, if it helps you think about it, just think of every function as being differentiable. But these are any nonlinear functions, not necessarily convex. So this is a generic nonlinear programming problem. Some other day I can tell you the history of why these things are called programming, but it's a nonlinear program. And we'll call it the primal problem. It's, of course, whichever version you want to call the primal. For the rest of this course, if it is written up nicely using that x with those constraints, we'll call it a primal problem. And x as notation is called the primal variable. Now, because I'm already using this word primal, I'm going to come to something called dual, which reminds me of a nice story I had read once. I think when Georg Danzig was developing linear programming, or had already kind of developed linear programming, back in the day, people used to write cumbersome verbose things like, so let this be the primal, no, they didn't call it the primal problem. So let this problem be the one which corresponds to such and such dual. So they didn't really have the word primal for the primal problem. They had a word dual for the dual problem because of Minimax theory that von Neumann already had studied in game theory in the 30s. So they always used to refer to it through a function pointer, like this indirect primal, whatever it was. Then one day Georg Danzig's dad suggested to him that, hey, you guys keep on talking about dual problems. Why don't you call your original problem the primal problem? And that's how the name primal problem was born. So we'll start by calling it a primal problem and say, there is then also a dual problem. And the dual problem idea goes back to, we can attribute it to others. I'm citing Joseph Louis Lagrange because his viewpoint of creating dual problems completely matches mine, or vice versa, mine matches his, is what he said in the introduction to a famous text that he wrote on analytic mechanics or whatever, that the construction that I'm showing you, first of all, I'm not going to illustrate any figures in this work. So, people who appeal to lots of pictorial intuition, sorry, Lagrange was not your friend. And then when he proposed this idea of Lagrange duality, etc., he worked through it and just created mechanized set of rules, you can say algebraic transformations, which seemed to work, but he did not really have deeper geometric or analytic explanation for what's going on. And means I don't really have a much better, other than what you see in textbooks, explanation of why we would come up with these duals. But let's gradually try to get a little bit of understanding about these duals. So associated to your primal problem, we'll attach something called a Lagrangian. So I'm trying to follow the convention followed by Boyd and Vandenberge in their book, because this convention is now very popular. So primal variables are written with x, dual variables or Lagrangian variables are written with lambda. There's a slight conflict with people in statistics or in several papers in machine learning where people use lambda as a regularizer, but lambda for us is a dual variable. And in statistics, people use beta as the primal variable, we use x. So just be aware when you read papers that these are the conventions at play. So because the original problem has disappeared, let me rewrite it here. We are minimizing. Again, everything today is in Euclidean space. So x is in R to the n, and you have m, so you have a finite number of constraints, okay? You can also consider problems which have an infinite number of constraints, but today we are not going to look at those. We'll look at only problems with a finite number of, say, nonlinear constraints, which will actually eventually be convex constraints. And to this, you define. So there are lots of sort of explanations of why Lagrange came up with that. They are with the benefit of hindsight. There is one version was going through indicator functions, relaxing the indicator function. This version is motivated in Boyd's book. There are several other ways, but those are standard explanations for this material in textbooks. I'm more interested in now just going through the mechanics that Lagrange went through to see how we can use these ideas. And so we define L of x comma lambda so when I'll just slightly not abuse, I'll just use this notation. H of x is the vector of h1 through hm of x. Just to have compactor notation, I'll write it like that. And we define the domain of this guy to be we will have the lambdas be non-negative. We'll quickly see why. Okay, so standard terminology again, these guys are called Lagrange multipliers. And now we set those lambdas to be non-negative because of this nice property that they bestow, is that if lambda is non-negative, for a feasible x, h of x is going to be less than or equal to 0. So if lambda is non-negative, lambda transpose h of x is going to be less than or equal to 0. Then clearly f is going to be bigger than L. So if you try to maximize, get the tightest possible value of the Lagrangian, this happens. If x is feasible, you get back f of x, otherwise you get plus infinity. Okay, so just slightly some more terminology, and pretty soon I'm going to stop with the terminology. Following Boyd's convention, though when I was writing the notes up, I felt a little disturbed by that convention. We'll write P star for the optimal value of the primal objective or the primal problem. I just got a little irritated by that because soon I'm going to show you a theorem, and so far we've been using stars to designate Fenchel conjugates, but this is the optimal value. So this overloaded notation you'll have to digest. So P star is the optimal value, and the proof is pretty straightforward, right? So remember, this is the Lagrangian that we are using. So if x is not feasible, sorry, that's a typo, that f sub I should be h sub I. So if that x is not feasible, then one of the hi's will end up being strictly positive. So you can set lambda to 0 in all the other dimensions except the lambda corresponding to this particular constraint, and when you take max supremum over lambda, that thing is going to explode to plus infinity. So the inner supremum can be made plus infinity. So by definition, by our conventions on how to play with infinities, fx is going to be bigger than that Lagrangian. And if x is feasible, then of course by construction, because lambdas are non-negative, and if all the constraints are satisfied, that product is non-negative. So the largest value, that particular Lagrangian term, so I'll just call this the Lagrangian term, because later we will use the word Lagrangian as sort of an adjective for several things. So if x is feasible, then the largest value that guy can take is 0. So you can put the outer inf around that. Yeah, that should be h. Like I said, the f of I should be h of I. So I've stopped writing slides, but because today I wrote slides, there are some typos in there. So in case that f of I should be h of I, to remind. Okay, so now just the simplest theorem, again so far super basic, but it's important to look at these things. So the primal value can be anything between minus infinity and plus infinity. So we allow P star to be minus infinity. So you can have a problem where the minimum is not attained, you just have an inf. That's why we allow a minus infinity in there. If there is not a single feasible x, then by our convention the inf will be plus infinity, so even plus infinity is allowed. So primal value is either a real number or minus infinity or plus infinity. And usually when we say suppose the primal is finite, that means it is strictly a real number. Then P star is that corresponding to the primal. So again, this is now, you can say either by algebraic playfulness or maybe something deeper is going on, but probably when this was discovered, deeper stuff was not yet recognized to be going on. So you are doing inf over sup. We might as well also ask what happens with sup over inf. And that thing is called dual. And the value, it can also be between minus infinity to plus infinity. That's called the dual value. Just like for the primal, we had the primal function. You can define, that's why corresponding the inner part. So before you take the supremum, the objective function of lambda that results, that's called the dual function. So that's our jargon, and this is standard result on called weak duality. Just look at the theorem. We'll obtain this proof. Don't look at the proof right now. We'll essentially obtain this proof as a byproduct. It's a very simple proof. It just follows by observation, but we'll try to prove it using some more higher power logic later. But important point for you to note that I'll write it down here. G of lambda is defined as, so it's in the original primal domain, L of x comma lambda, which is equal to So the dual value function or the dual function, we'll just call it the dual usually. There's just pointwise infimum over family of linear functions indexed by x. So by construction it is concave. So regardless of the concavity or convexity properties of the primal objective function, the dual objective function is going to be always concave. And you're trying to maximize it. So maximizing a concave function is like minimizing a convex function, so you're happy. And this happiness is used by people to derive some sorts of bounds when you relax difficult nonlinear problems by looking at the Lagrangian and then trying to get a dual. Then they try to say that, okay, we'll solve a relaxed problem because at least the relaxed problem is convex, we can solve it. But the entire hard work there is, even though you relaxed it, how well did the relaxation perform on the original problem? So, but the weak duality theorem says that the primal objective function value or the primal or the value of the primal p star is always at least as big as the value of d star, the value d star. And there's actually, this is one of those proofs where there's hardly anything to prove other than just play with notation. So that's why I put it in small font here, but you should just try to verify that yourself. And more interestingly, you should do this exercise. So if I show slides, or also I do that during the lecture, I mention sometimes exercises, and either you could try those when you go home, or you might meet them on a homework, in which case you'll try them anyways. So it's good to just try this out. And this exercise, all it's saying is just derive this weak duality theorem, where instead of just inequality constraints, you also allow equality constraints. So whatever little Lagrangian and p star d star we derived right now, the same thing, there we had assumed that we have inequality constraints. Try to just go through the same procedure and show how to come up with a Lagrangian when you also have equality constraints. And the rule of after you've gone through this exercise, then you're allowed to just remember it. You don't have to derive it anymore, that if you have less than equal to constraints, your corresponding dual variables will be non-negative. If you have equality constraints, then the corresponding dual variables are free to range over R, which comes as a byproduct of this theorem that you can prove. Okay. Any comments so far? So, as a slight verbiage, I call that thing weak duality, right? P star is bigger than equal to d star. So, of course, every normal person will wonder that we have shown p star minus d star is non-negative. Actually, this is a bad way of writing. I shouldn't have written it with subtraction, but I should have just written p star bigger than d star. But we say that our problem has strong duality if p star is actually equal to d star. And the reason I said I didn't want to write p star minus d star is in case I'm trying to subtract infinities, which I didn't want to do. But otherwise, this always holds, which tells us if p star is always bigger than equal to d star, if you have a problem where p star actually goes to minus infinity, that shows you what should happen to d star, right? If primal becomes unbounded because p star is bigger than equal to d star, what happens? D star also should become unbounded, otherwise your weak duality won't hold. So the interesting question now is, how can we try to conclude what properties must our optimization problem satisfy so that we are guaranteed that p star will actually equal to d star? And thinking abstractly, you may say we care about this because we'll soon see. It shows that you can rewrite the problem, and often Means the reason I'm going through this slowly is whenever you're working with optimization problems, do not forget to try solving the dual. It happens even to the most experienced people. You will see papers written in NIPS conference here and there, or in machine learning journals, or even in optimization journals, where people go through a lot of hard work to solve a humble little primal problem, and then maybe later 5 papers down the line, somebody realizes, oh, if I had actually just solved the dual, it was much easier. Has happened, okay? So it's important, whenever you're considering a problem and you're stuck at it, try to look at its dual. Can often really help you. And quite interestingly, if you're looking at the dual, you want to know, does strong duality hold? So that solving the dual is good enough. So unfortunately, for general nonlinear programming problems, the same difficulty arises. We don't have an easy set of necessary and sufficient conditions that guarantee strong duality. There are several known sufficient conditions. I'm going to mention one of them in a theorem soon. And you might have heard of conditions like Slater's constraint, qualification, and so on for convex problems. Okay? In the non-convex world anyways, we don't really have a very functional, you can write a theory of duality, but it's not so usable because all the quantities involved are essentially uncomputable. So, but you can write it for prettiness of algebra and to maybe get a higher level perspective on your problem. So let's try to look at a generic duality theorem. And this generic duality theorem I just picked out because it looked nice and it shows us a place where we can show off a little bit of our Fenchel conjugates. I'll go through the proof of this thing on the board. And it also shows us an example where function being equal to its biconjugate at a single distinguished point is equivalent to strong duality. So let's actually go through this slowly. I'll leave the statement of the theorem on the board, and let's try to prove the theorem. So define V as the value function. M is the number of constraints. So I try to follow the convention in the class that for me little n is the dimensionality of the primal variable. M is the number of constraints and hence the dimensionality of the dual problem. So let V be the so-called primal value function. That is, V is defined as the value of the primal objective. What I was writing HI, right? HI of X is less than equal to UI, 1 is less than I is less than M. Or in vector notation, that H of X is less than equal to U. So just by this notation, the first line, that P star is equal to V of 0 is just by definition, because P star is the value of the primal optimization problem. So V of 0, that's what it is. The other two connections are more interesting, and that's why I mentioned earlier that I'm a little unhappy with the stars. This star is a Fenchel conjugate. V is a function, and V star is its Fenchel conjugate. V double star is its Fenchel biconjugate, because V doesn't have to be convex. So that's why we write V star star. So, but P star and D star, there are numbers, or maybe extended numbers. So let's try to prove that V star, the conjugate of the primal objective value, is nothing but the negative of the dual function. So we try to prove that, okay, so by definition, V is the infimum of that set. So we are just taking its Fenchel conjugate by definition, which will be just the supremum. Right? That's by definition the supremum. That's the definition of Fenchel conjugate, which looks pretty. So now Hx being less than equal to u is the same as there exists a non-negative vector z for which Hx plus z is u, right? So v of x, v of u is just f of x, where that certain nice property for the x's for which, so x has to be in, say, domain of f, and z has to be non-negative, and u is like that, right? So that's just so far just using the definition of v. The only interesting thing we did was introduce that extra variable z. That thing is also called a slack variable. You might see that being introduced as a common trick to get rid of inequality constraints, to replace inequality constraints by equality constraints. So that's a standard trick.
It should be in over f of x.
Pardon?
In over f of x.
Oh, okay. So the way I wrote that is, it's kind of okay. Let's see. See, there is the minus and there's a sup here, right? So v of u is inf over f of x something, right? Then we have a minus v of u there, and there's a sup outside.
That sup is also over x, is it? No, that sup is over
That sup is over the value of those all the possible values that that set can take.
That sup is over u, right?
Yeah, that's the only variable in there.
But v of u itself is inf over all x of f of x, such that h of x plus z is equal to u.
Wait, so you are saying that
The outside sup is over u.
well, the okay, outside sup is over all possible values that this can take, and that is actually over u. The inside one, this one now, is actually over u, x, and z. And because it's over u, x, and z, it encodes the v of u inf. So it's over now 3 variables. That's why I explicitly wrote the extra variables in the supremization there. Yeah, too much of a shortcut. One more step I could have added in there. So u is just that guy. So just plug in that value of u in there. So we have eliminated u, so only x belongs to domain of f and z show up. So now I'll just collect the x variables together and the z variables together. That's all I'm going to do now. So I pull the minus outside, the sup becomes minus inf lambda transpose h of x plus f of x, and supremum over, this is over Z, minus lambda transpose Z such that Z is bigger than 0. So I just broke the soup into two parts, the parts that depend on X and the part that depends on Z. That's all I did there. This guy in there is really nothing but your Lagrangian L of x comma lambda. And when you take its infimum, that gives you the dual function g of lambda. So this is nothing really but, so the first part is nothing really but minus g of lambda. So it's, don't read it as an equality yet, plus something else. So the second supremum, it becomes plus infinity as soon as even a single coordinate of lambda can be negative. So the only time the second supremum does not blow up is when lambda is non-negative. So this might be viewed as an indicator function. That's what indicator functions do, right? Either they are 0 or they are plus infinity. So that means this thing, that upper line is exactly equal to minus g of lambda for lambda bigger than equal to 0 or plus infinity otherwise. Okay, so that gives us line number 2. The last part that remains is so the last part actually follows fairly straightforwardly, but let me write it down for you. So the dual value d star, what is the dual value d star? Is just the supremum of g lambda. So I flipped the signs. This is minus inf of minus g lambda, right? I just added and removed, I just added and removed the minus sign there, which is then nothing but minus the inf of v star minus lambda, which you can, by definition of Fenchel conjugates, verify that it is v star star of 0, because after all v star star at any vector theta will be just, you know, supremum of theta transpose whatever lambda minus v star of lambda. So here this is with minus lambda, because minus lambda is, so that's equal to v star star of 0. So that's how you get the entire theorem. So what does this theorem actually say? Now look at the theorem. It shows you that if you are in the lucky circumstance that the value of v, the primal objective function value p star at 0 is the same as the value of its Fenchel biconjugate, then we have strong duality. And this is a very generic kind of theorem. Any problem for which you can establish this, you will have strong duality. Convex, non-convex, okay? As long as you can establish this. Of course, the badness is, like I said, is generic, but maybe not entirely useful in this form. So there are 5 or 10 other forms related to this abstract strong duality result, which might give you more convenient ways of verifying this. But I am just abstracting out and showing you that strong duality kind of can be set up on a fairly generic pedestal, and depending on your specific problem that you might face, if it's say not convex. So the only reason I'm highlighting these results is because I'm thinking maybe you will encounter some non-convex problems also if you can show this. And sufficient conditions like Slater's constraint qualifications, they ultimately ensure that, so there's a corollary to this that's in, I don't know, okay, it's in the book that I have there. So there's a corollary to this, that if the value function v is lower semi-continuous at 0 it's only 0. So that means its graph might look like this boundary point is actually included and this one is not. Then it will be finite at that point, and if it will be finite and it will have a non-empty subdifferential. So each of those statements actually is a theorem in convex analysis or general analysis of subdifferential functions. So we are not going to be able to prove all of those, but I'm just trying to point out to you that generic things like Slater's constraint qualification, they ensure ultimately that this happens. So Slater is stronger than this. And what is Slater's constraint? I'm not going to again prove this. Maybe we see, however, this last line that I've written here, that Slater's so-called constraint qualification that we'll see soon actually implies that V of 0 is V star star 0. That we might see on an exercise on a homework. So just to tell you what exactly the theorem is, and this is by far one of the most popular conditions for convex problems here, which implies that generic duality result. But like I said, because this is stronger, people have also studied on several examples of other sufficient conditions which are weaker than Slater's constraint qualifications. And if you happen to be dealing with an optimization problem for which you are unable to show Slater's condition holds, but you still need to rely on strong duality, think of this theorem and think that yes, there are other weaker conditions than Slater which might still give me strong duality, okay? But Slater's condition is ultimately here for a convex problem, and it's actually quite strict. It just says that you should have a strictly feasible point. I'm just citing it here because this is often used, and most of the optimization problems that we look at, this condition is relatively easy to satisfy. But let me show you a pathological example where it doesn't. Yeah.
So right at the end you say the dual optimal is attained by E.
That means it's non-infinite.
Okay, that's typically not what I think of. Typically I think that means that the infimum or supremum is attained by some point.
Mm-hmm.
So am I thinking the right thing here?
So you are thinking the right thing, that there will be a point,
Right.
lambda star, which will give you D star.
Right.
That's what I mean.
Okay, but
Yeah.
then you wrote D star, the actual value. See, I view it as the dual optimal being attained as a statement about a point attaining a value, not about the value being greater than negative infinity. Maybe I'm just reading too much into your IE at the end there. I just don't see that those two, that the math at the end is equivalent to the statement right before it.
Okay, I see this. This kind of stuff also, I've seen this happen. So the value might be, there might be no points which actually give you that.
Well, sure, in semi-definite programming,
Yeah,
it happens all the time.
Yeah. So here I actually mean that there will be a point that attains that value.
Yes.
So I should remove that IE, I should qualify that.
Yeah, it's just a different thing.
No, it's a very important point, because not only in semi-definite programming, I'll show you an example from your world of something like, okay, this is convex, but my example is non-convex. So let's look at a convex example where this fails. So, but I hope everybody heard Shiva's point that just because the dual optimal value is bigger than minus infinity does not necessarily mean that there is a lambda star which will give you that particular D star, right?
Yes.
And however, we can exclude that maybe somehow by one more assumption. Yeah, but it's a very important point. Yeah.
So I think that Slater's condition is that, that strong duality holds, and if the dual value is finite, then it is attained.
Okay.
It's kind of it's a convex combination of what you said and what he said. The dual like the dual value is not guaranteed to be greater than minus infinity as you said, but if it is greater than minus infinity, then there is a point that attains it.
I think the version that I wrote ensures that there is a that it is bigger than minus infinity.
Doesn't strong duality itself imply that the points are attained?
No, strong duality could be both are minus infinity or both are infinity.
Okay,
Yeah.
that's fine.
That's different. That's different statements.
Those are not pathological, so those happen.
Right.
Like I can construct linear optimization problems in which
Yeah.
the primal and dual are both minus infinity or both plus.
That's
That's
a separate question. That's a separate thing. So that's the values of the program.
Yeah.
As opposed to the points attained.
Yeah. So then, and so the status condition says that if the dual value is finite, then
There is a lambda star that attains it.
So it's not always attained or it's not always finite, but if it's finite, then it's attained.
Yeah.
Okay, so I think coming back, maybe the proof for that would be that then there will be a point where this guy will have a non-empty subdifferential, which will mean that there is a point which actually attains the value for us. So there is a longer conclusion hidden in there, which will boil down to actually this theorem being invoked to prove what he just said. But it's an important point. So I'll send out an email to clarify so that I don't tell you anything wrong. But let me show you an example of where this later guy fails and we don't actually have strong duality. This is already one of those pathological looking examples, right? We are trying to minimize e to the minus x subject to that constraint that you proved to be a convex constraint on the homework. So the domain is x comma y, x is a real number and y is strictly positive. Well, e to the minus x is already bad to see there, right? Because e to the minus x can be driven towards 0 by letting x go towards plus infinity. That's the bad thing about it. So the only feasible point is x square y because it's going to be less than or equal to 0. The only time that will be not, the only time you can make it feasible is if x is 0. So, and for x equal to 0, p star is 1. Now, let's try to make the Lagrangian from that. So Lagrangian, let's make it mechanically. X and y are the primal variables. Lambda is my dual variable with non-negativity constraint. So you compute the dual objective function by taking that infimum. So the dual problem then turns out to be nothing but, the dual problem is a maximization problem. So this infimum equals 0 for all dual feasible lambdas. So the dual problem is maximizing g of lambda. That means maximizing 0 over lambda, and the maximization is then d star is 0, but p star was 1. Thank God I don't have to deal with such pathological problems, but they can happen. Okay, so now I think after stating those couple of things, let's just work through some simple examples. So some of you have certainly seen this kind of derivations of duals. For those who have not, let's just quickly go through a couple of important examples of the kinds of problems you see all the time in papers. So one of those is, this one is actually called Rockefeller's problem. These days it's called something else. Maybe people call it the ADMM problem, but Rockefeller looked at these problems in great detail back in the day. And here we are just going to mix your Fenchel duality and Lagrangian duality. Let's quickly derive a dual to this problem. So primal problem fx plus r of ax, henceforth f, all the functions until I come to Minimax theory, all the functions, please assume them to be convex. And I'm trying to I made it slightly more complicated to give you a domain. Y is just the range of A. So let's try to get a Lagrangian dual for this. So how should I get a Lagrangian dual written in terms of the Fenchel conjugates? Fairly standard exercise, but it's good to know how to do this, because now and then you might have to do it. So the idea is fairly standard. So we'll see another example of this. So I introduce, so far, yes, so the reason I'm mentioning this is, written up there, it's not written in the traditional constraint form in which I introduce, right? Minimize f of x subject to h of x less than or equal to 0. So I'm just going to inject another constraint in there if you want to think of it mechanically that way. So to derive that, so let's introduce another variable, y is equal to ax. So we get, so this highlights a very important point when writing optimization problems. Often, to simplify what your problem looks like, it may be worthwhile injecting in new variables. And we'll see more examples of this down the line, that this very simple idea, which of course anybody would have, is actually a very fruitful idea. It goes really far. I'll describe to you even parallel optimization and so on, which ultimately rests on this simple decoupling idea. So you introduce that additional variable, and now you have constraints. Fine, now you write your Lagrangian. X and y are primal variables. I'll write new. Lambda I try to reserve for inequality constraints. Nu I write for equality constraints. Again, this is Boyd's convention, so it keeps life simple to follow some convention at least. So that's your Lagrangian. I just called it partial Lagrangian because there I wrote a slightly more general version with those unnecessary x belongs to script x and y belong to script x constraints, not so important. So from this Lagrangian, you know how to now pull out a dual, because our dual will be given by, it will be a function of the Lagrange multipliers or the dual variables. By minimizing your friend the Lagrangian here, right? And after that, it's just moving around terms and doing simple algebra. Let's see. I can just write it there because I don't have to repeat the derivation. It's actually straightforward, right? So I just rearranged that guy to do the same thing that I did before, put the x terms together and the y terms together. Infimize. Write inf of something as minus sup of minus something. That's a very common way to bring in your friend the Fenchel conjugate. So you just did those double switching of infs and sups, and now that stuff is apparent to you in terms of Fenchel conjugates, right? Because this is sup of some linear term involving f of x, so that will have an f star in there. That is sup of r with some linear term, that's r star. Just throw those in there, and so the dual problem is trying to maximize g of u. That should be u, sorry, typo. So you get an equivalent dual problem. So let's look at a much simpler, shorter example of this. Again, we'll work through, this is a more technical result. I'll come back to that after some time. So let's look at an explicit example of when you use this. So this is a so-called norm regularized problem. Often we use L1 norm, or you saw on the homework these LPQ norms as regularizers, and Some people use total variation, some people use all sorts of other norms, structured sparsity norms and whatnot. These keep coming up in machine learning applications. And several of these norms can be written, or the regularizer can be written as a linear operation on x, and you take the norm of that. So this is a typical example of that f plus r of ax problem. And now you've already seen how to get Fenchel conjugates for that, so you can get the dual problem. So the dual problem is as expected. You have f star up there, you're trying to minimize. The dual problem was a maximization problem. I got rid of the minus sign and wrote it as a minimization problem. Can anybody tell me what is that y star down there doing there?
The dual function of the norm is the indicator function of the dual norm.
Okay. So the mnemonic is the dual of norm is indicator function of the dual norm ball. And that's what you're seeing here. So this is a special case of this general dual that we derived on the previous slide. Okay. And again, means the slides contain some theoretical results which guarantee when actually primal and dual, when strong duality holds in these problems. So another example, now written more generically without that extra a in there, is this thing. This idea of injecting new variables is so popular, people give it a name. It's called variable splitting. So you have fx plus h of x, and again, I am using the convention of not using g of x in the primal because we are using gx as the dual. Later we'll maybe drop even that. So for this now you can, I guess, follow, just recreate the derivation that I did, but it's worthwhile. If you have never done variable splitting before, just go through this 1 minute long exercise yourself to take fx plus h of x and decouple. And the bigger picture, why do you actually want to do this? Well, f of x might be, say, suppose you have f of x were something like this, x square, and g of x is something like, whatever. G of x is, this is f of x, and this is h of x. F of x is an easy function to deal with. This guy is a complicated function. So whenever you have a combination of, say, easy and complicated functions, sometimes you can make your life easier by introducing new variables that allow you to decouple. The same variable, if it occurs in both f plus g, f plus h, might be difficult to minimize the sum of f plus h, but sort of handling f separately and h separately might be much easier. That's why you introduce new variables. We'll actually do this in great detail later. So you should go through that little exercise. And I'd like to actually also mention to you today something more general, maybe a more abstract way of arriving at duality. But at this point, do you have any questions? So I just showed you some simple examples of getting conjugates and duals. Maybe during some of the recitation, if you go there, you can work through explicit examples of deriving these things, or you might derive some interesting duals on your homeworks.
Yeah, the counter example you showed, so I didn't get the part that why was it such that it failed?
Oh, so that counterexample was just a counterexample where Slater does not hold, and you happen to not have strong duality.
Okay.
Slater's failure is not, Slater is just a sufficient condition. So you could still have strong duality, but that was an example to show, no. And that's what I said in the beginning when I started talking about strong duality, that we do not really have easy, necessary, and sufficient conditions for strong duality. So, which is why hundreds of papers get written on trying to come up with complete descriptions of strong duality in different settings. Okay, so the final thing I want to mention is maybe at a more abstract level, the idea of minimax. And I thought I'll mention it here because maybe at some point we might see an application maybe to game theory or Nash equilibria or something. So it's good to have already seen this here. Or maybe even if you don't see those fancy applications, we'll see some other generic ways of proving minimax theorems. Today I'm just going to state the theorem or even just the description. And the way I describe these things is I'm trying to encourage you to, okay, these are well-developed concepts, but just to encourage you that, you know, many of these far-reaching ideas can be attained, or you can start attaining them once you start playing around with the common objects that you had been dealing with so far. And what I mean by that in the case of minimax is, again, this is a whimsical introduction to minimax. It's not necessarily the correct way, but let's have it anyways. So suppose we had some function phi of xy from some arbitrary sets to the extended reals. With such functions having two arguments, so far we've done many different things, right? So one of the things that we have looked at is this marginalization, right? And we saw that in the first line phi is arbitrary, but we saw that say phi is jointly convex in x and y, and you marginalize out one of the variables, the resulting f is convex. And after that, you even considered minimization of that f. So in some sense, in this algebraic sense, we are looking at inf over x, inf over y, phi of xy. So that's a class of problems we've already looked at when it's jointly convex. Now, another example that we looked at when we constructed convex functions, and in special cases we constructed Fenchel conjugates or support functions, then we said, well, let's look at f of x obtained by doing sup, and there we said, suppose phi of x is phi of x comma y is convex in x for any arbitrary y. Y can take values in whatever set, and then you take pointwise supremum, f of x ends up being convex. And so you could again talk about doing inf over x of f. So this leads to this has led us to inf sup. So what remains is another class, right? Sup of inf. You might also think of those problems. And so this is what I'm saying. We looked at two already. The third one, we have actually looked at it today when we looked at Lagrangians and duality theory. So we could also equally consider sup over y, inf over x. Minimax, max min. So that's where the name minimax comes from, by looking at both versions of the problem. And if you look at things purely algebraically, with the kinds of operations you had been successfully doing with these, you can say, bivariate functions, it's fairly natural to come up with sup inf, right? And of course, then once you come up with that, if you stop, then we haven't gained anything, but then people investigated a lot of properties and discovered that actually these two viewpoints are nice. So let's look at why they're nice. So the first one I mentioned, this is what I written down here, sorry. So
just to be clear, can you clarify, whether phi is convex in?
no, right now it's arbitrary. So on this slide, phi is arbitrary, x and y are arbitrary, phi is arbitrary. But in the inf example, x and y are convex sets, phi is jointly convex in both. In the sup example, set y is arbitrary, but x has to be convex, and phi has to be convex in x for every y. In the third example, x has to be still convex.
My question was, if phi was like, say, concave in y for all x, it's the same problem.
Yeah. So yeah, in my notation, okay, in that notation, we are going to, whenever I take an infimum over somebody, that problem for me is going to be convex when I qualify, as soon as I make a qualification of convexity. Yeah. Okay, so the Minimax world begins by asking the question that does the order of this optimization matter? When is inf sup equal to sup inf? And people have invested a lot of effort into trying to answer these questions. Huge amount of effort. And all the theory of duality, KKT optimality conditions, etc., both in finite and infinite dimensional spaces, can be obtained by just looking at theory of Minimax. Maybe next lecture I'll derive. I don't know if it's a fruitful use of our time for me to derive KKT conditions for you, but maybe I'll show a short proof, the non-traditional way of getting KKT optimality conditions as a special case of the Minimax theorem. Okay, so weak result of Minimax. Weak Minimax is nothing but big notation for what we've already done. We proved something called weak duality, and weak Minimax is essentially weak duality. It's saying that if you first infimize and then take the supremum, that value is going to be smaller than first maximizing and then minimizing. And the proof is actually simplified remarkably once you just introduce new notation. So write f of x to be the function that results by marginalizing out y, and g of y as the function that results by marginalizing out x. Right? And then just by definition, you see that f will be bigger than phi, which will be bigger than g, because f is taking sups and g is taking infs. So this has to be true. And because this is true for all x and y, a very nice way, this is a device you might use in your optimization problems, right? An inequality that holds over your entire set can be written in another way. It also holds for, depending on the direction of the inequality, it also holds for the min or the max. So whenever you have an inequality that holds for an entire set, you can compactly write it by introducing min and max. So you take inf over x here, you get that, and you take sup over y on that side and you get that, and you have weak minimax. And homework exercise for you, this one I think I will put into this I'll actually put into the homework. So you have advance notice of homework. Just derive the weak Lagrangian, the weak duality theorem that we had for Lagrangian duality as a consequence of this weak minimax property. And there you'll see that you can obtain that by setting phi equal to actually the Lagrangian with a careful choice of the second variable. That's pretty much the answer. So by definition, whenever, So now Shiva's point becomes very precise here, as in people do worry a lot about those things, which is, of course, one should worry about those things. So if inf sup equals sup inf, you can flip those. The common value of the object is called saddle value. And if there is a saddle, if there is a point, a pair that actually exists, x star comma y star, for which that value is attained, you say the value exists. That's just the verbiage there. And that is called a saddle point. And the definition of strong minimax is the following, or this is, means I just write it as definition, is that, you know, phi is as before, and there is no restriction on convexity and concavity, okay? Phi is free right now. And we say a point x star y star is a saddle point if and only if the inf is attained. So usually when I say inf is attained, I mean inf is attained at x star, and the sup is attained at y star. That means you do have a saddle point. There's an actual pair x star y star, and that these two extrema are equal. So then we say we have a saddle point, which means x star belongs to the argmin set, y star belongs to the argmax set. And whenever, instead of inf and sup, we write min and max, this is implicit that x star and y star actually are there that do it for you. So all of this is so far just playing with algebra, right? And the important question, the $1 million question here is not whether you can construct saddle points for arbitrary fees. The question is the converse of that. What kinds of nice fees do we know of for which saddle points will exist? And your Lagrangian is one of those types of fees. So the more interesting question is, you know, if you're working over optimization problems in some space X, that's the primal space, how to come up with a companion space Y for which we can have this saddle point. And again, all of this is with the benefit of hindsight, because we have seen, maybe I didn't show that enough, but okay, the world has seen enormous utility of Lagrangians. So just that bivariate function is extremely useful. I just showed you some trivial examples, but those are used all the time in research, so those suffice here. So really the interesting question is, starting from the primal space, how to introduce some useful function so that we do have a saddle point. Just to, again, maybe I think of this with maybe an engineer's eye, that I just want to rewrite my problem maybe in 5 different ways, and maybe one of those ways makes it easier to solve the problem. And the theory of duality is just giving you one family of principled ways of rewriting your problems, okay? You can create other families, but this has stood the test of time. So here is, just for reference, I'm writing down sufficient conditions for the existence of a saddle point. Maybe later in the course, when I cover fixed point theory, I might cover for you a proof of these things, of the existence of saddle points. And the existence will hold in fairly general situations, but for that we'll introduce some interesting fixed point theory. Okay, so just a quick example and then we are done, to show you how I use this minimax. I look at your friend, the Lasso-like problem. I just call it Lasso-like because there's no square up there. So P star is the minimum value of that. Now again, this guy is written as an unconstrained problem, but because it has all sorts of norms in it, you can rewrite the norms maybe using, whenever you see a norm, always think, does it help me if instead of the norm I write it as its dual norm, or do I write it as its conjugate, whatever, does it help you or not? So X, the one norm, has this representation, because one norm is dual to the infinity norm, 2 norm is dual to itself. So if you see one norm, you can write it using that max. So you have a min there and a max there. So you can actually write that problem as a min-max problem. So that's one natural way in which that saddle point function phi of x comma y comes in. That you actually started with some compact notation and injected an extra variable. It's the same idea all over. You inject extra variables to somehow decouple things and maybe make problems slightly simpler. It need not always make your problem simpler, but it's worth a try. So the one norm has been replaced by its saddle point representation, and then we pray and hope that min-max can be switched around, and for that we have to invoke some theorem which allows us to do that. Essentially here Slater will help you because these are essentially linear constraints, we have to worry about this guy. So if there's a strictly feasible U, just a single strictly feasible U that exists, which does here, you can actually flip things around. So this is really going through the algebra of these convex conjugates. But the point is, this is one way. Whenever you deal with an optimization problem that has a norm in it, there are several ways of writing duals by creating a new variable, taking Lagrangian and doing that variable splitting, or some people prefer this way, but you might see both of these ways in papers. So, and this is by just writing the norm by its dual norm. And yeah, means the rest is just an exercise, and you end up taking that primal and formulating actually a dual optimization problem. This dual is, what kind of optimization problem is it? Amongst the class of optimization problems that we have looked at, well, if this were not there, it would be essentially a linear program, right? But you have that there, it's like a second order cone program. So fine. I don't know, probably you covered some things in recitation, okay.
This is SOCP, but it's also QP if we add a square term in the constraint.
If you put that square in there.
Yeah, but we can transform this to a QP trivially by taking the square on both sides of the constraint. And then put a dummy variable and put that quadratic term to the objective function, then it becomes a QP standard.
Did you go through the example? Yeah, okay. Because I don't know if you've looked at the slides. I have examples for you which show that even though QPs can be written as SOCPs, not the other way around.
Yeah,
but means for this I'm saying, but in general one should be warned about that.
I'm just not because there is an L1 norm, right? L1 norm is just a sum of absolute value, and you can decompose it. You can even reduce it to LP if it's just an L1 norm. So just spread it, yeah. So basically you have a positive path and negative path.
So, but anyhow, you should convince him of that because in general you can turn quadratic programs into second order cone programs, but not vice versa. Okay, but the thing Yu Cheng is also mentioning is this constraint. There are several ways to handle that. Is by really introducing a new variable w, where wi is the absolute value of x of I. Then L1 norm becomes just 1 transpose w, and this constraint can be turned into a bunch of inequality constraints, etc. But those are like standard problem transformations. If you go through the slides that I've linked on the class website, you'll see examples of all these things. So I really expect you to have gone through all those things so that I don't have to spend time covering that standard material. Next time I hope to cover this. I'm out of time. That this is just an advertisement for next time. We saw very simple Fermat's law that optimality, necessary insufficiency of optimality could be characterized by 0 belonging to the subdifferential of your function. And ultimately, the KKT conditions are nothing but 0 belonging to the subdifferential for a suitably chosen saddle point function phi. But I'll actually go through this example, I hope, next time to show you a different way of deriving KKT conditions using the notation that we have studied so far. Okay.